Okay, thank you. Uh, Today I am going to show you experimental results from my group, both spectroscopic experiment which is from Raman scattering and also some magnetotransport experiment. Okay. So first the question was RuO2, very famous compound. By now you know that whether altered magnetism exists in RuO2 or not. So the result is we didn't find any indication. Of course, it's a different technique. We wanted to find out spin phonon coupling, but we didn't find. But we found electron phonon coupling that I'm going to talk about. And another topic, the result. Suppose you grow strontium ruthenate, very important canonical system. It's a topological system, and if you measure along two crystallographic direction, the resistance versus temperature and magnetoresistance, whether the properties are same or not. Okay, these are the two simple questions. So coming to this altered magnetism. Okay, so we all know ferromagnet when all the spins are aligned in the same direction. And what is the this is real space, and in the K space there will be splitting of the band, spin up and spin down bands, independent of the Q vector. There is always a splitting. Now in case of antiferromagnet, these are anti-aligned spins, but in the band structure there is no splitting. But now comes to the altered magnet. It looks like antiferromagnetic arrangement. Of course, in their local environment, this is anisotropic spin, we call it. And in the band structure, there will be splitting. It's like a splitting, these two splitted bands will alternate, but there must be some splitting. So what is the important glue in this system? Important glue in this system is that there are some sort of magnetic order. There will be some exchange interaction, right, between these two spins. And if there is exchange interaction, then phonon can interact with this exchange interaction via spin phonon coupling. And if you prove there is a spin phonon coupling, then you can say that at least RuO2 that we are interested in is magnetic. And of course, measuring RuO2 is not enough. So we had to measure several compounds in order to make some reference frame with respect to Raman scattering measurement. So what we did, we took metals, RuO2 metals, IRO2 metals. These are all rutile structure, and we have also taken TiO2 and SNA2 insulators, and all are paramagnetic in nature. Okay. Now this is the data from 2017, where this is basically the title of this PRL paper, Itinerant Antiferromagnetism in RuO2. It's a bulk single crystal measurement. So we digitize the data at high temperature. I am showing it here. Susceptibility and temperature, magnetic one. Now, if you cool down, the susceptibility is going down. So natural explanation would be that magnetization is decreasing because antiferromagnetism is coming in the picture. But this is not the right explanation for all compounds. So if you measure also at low temperature, this is our data, we found the paramagnetic behavior. That is also reported, it's not something new. And we have also seen the upturn. Okay. And these red lines is the fitting with the equation. This is simple C by T law. And the theta will be almost 0 Kelvin because it's a paramagnet. And there is a scaling, you can see. This scaling, this entire discussion about the magnetism in 4D and 5D metals are discussed in 1976. Very old discussion. And this scaling is the Fermi liquid scaling. Okay. So in case of Fermi liquids, the magnetization actually increases when you warm up the system. It's not magnetic moment is increasing, but there is a scaling factor, and T star is the Fermi temperature, and the dependence is T square. Okay, so that is the explanation. It's not antiferromagnetism, it is simply Fermi liquid metal. Now, we studied the phonons, and this is some sort of the schematic of our home built Raman scattering setup, and this is the how experiments look like in real life. Okay. So this is a representative data of ruthenium oxide, low temperature and the high temperature, and the corresponding data for TiO2. So one thing you can see that this data is noisy in the case of metal. This is natural. In a metal, the light doesn't penetrate much and the phonons are dressed, and that's why the weak intensity comes in. But at least what I have EG and A1G modes. I can resolve it, and the corresponding modes are also intense in TiO2. I can compare them. And what you can compare them? The phonon frequency. For an example, this frequency of this phonon, how it changes with respect to temperature in both compounds. And this is for the metal, RuO2 metal, IrO2 metal, and this is for insulator TiO2 and SnO2. When you look at the data, you see that when you cool down, the phonon frequency increases. This is very normal phenomena. So you have a crystal, you cool down, it contracts, so the bond strength increases and frequency increases. This is natural. But when you look at the numbers here, that how much it is changing from room temperature to low temperature in all these compounds, then there is a pattern. For an example, in the metal case, the frequency change is about 6 centimeter inverse. But if you look at the insulator case, is 1 to 3 centimeter inverse. This is for the EG mode. Okay. Now let's look at the A1G mode. The same thing is also happen for the metal case, is 7 to 10 centimeter inverse change, and in the insulator case 1 to 2. So now I combine all of them. We also measured the line width. So we have a combination figure. So left axis is the change of frequency and the right axis is the change of line width, how phonon narrowing, and every ellipsoid represents the pair like EG mode and A1G mode. Now look at this black one, the frequency change. If you look at the frequency change, see, this is for the metal, this is almost the range, and now for the insulator you are somewhere here. So very distinct difference. Two classes are emerging depending on metal or insulator. Now look at the line width here. In the line width I don't see much trend. Okay, I cannot really say this is for an example, IrO2 is a metal but TiO2 is an insulator, but they are similar. So there is no pattern as such. So this we try to explain what is available, that is a Clemens model, and in the Clemens model that you are creating a phonon at zone center. So this is the wave vector 0 and the frequency, and now it decays through acoustic phonons, and acoustic phonons will have opposite momentum because plus q and minus q, if you add up you will get 0 momentum, and omega q will have basically half of this frequency. And this is the natural, this phonon frequency will increases as you cool down and line width will decreases as you cool down. So what we found that this is the Clemens model, as you know, and Kramer's conic transformation of the gamma will give you the frequency, and whoever does Raman scattering, these are basically, you don't look into the formula, this is like a textbook example, but what we found that these D and C are not independent, and if you try to fit your data with these two equations without paying attention, then you will be able to fit, but the outcome, the results, the parameters will be very wrong. So because D and C are interconnected, and this is the formula for D and C, Kramer's conic transformation give, and lambda is some sort of dy frequency. So randomly you cannot choose C and D. So we could not fit if you would pay attention to the C and D, and then we found that how to feed the data for metals, and the frequency change depends on the phonon self energy, and the line width also depends on phonon self energy. And in the case of metal, not only phonon interaction happens, phonon metal like electron interaction also happens, so you have another self energy terms coming in the picture, and this is the phonon self energy if you have electron phonon interaction. This is not our invention, it is there in the paper, so we just used it. So what is important here, this G is the electron phonon interaction. If there is no electron phonon interaction, G will be 0. Then you come back to the phonon scattering model, and this F parameters is basically Fermi Dirac distribution function. This Fermi-Dirac distribution function is required because you are changing temperature. So you are changing the population of the electrons around the Fermi surface. Okay. Now, if you use this self energy, what we got in the frequency expression, there is an extra term coming is kT square. Okay. You might say that in the Fermi liquid there is a T square term, right? In the magnetization data there is a T square term. Now it also phonon has also T square term. This is the pure result of Fermi-Dirac distribution function, nothing else. It's like a phase space scattering things. Now in the line width we didn't see anything. There is no extra factor coming in, and that explains our data why the phonon frequency change is different depending on the metal and insulators. And I will just briefly tell you that the fitting quality. For an example, IRO2 is a good metal, and if you use only Clemens model, only phonon-phonon scattering, in the low temperature range you cannot really get this parabolic nature. But if you use the T square term, then you are able to fit data nicely. And of course the C and D parameters are not independent parameters. We basically followed the same scaling for C and D. Okay, so now you can see around 100 Kelvin where there is a magnetization change here. There is nothing is happening in the phonon frequency. It's just a smooth change. So that means there is no magnetism that phonon is talking to. So spin phonon coupling is absent. That's why we tell that there is no trace of magnetism. In bulk RuO2, single crystal RuO2, there is no magnetism, no altermagnetism. But if you grow RuO2 thin film, then the altermagnetism coming in the picture. Okay, so defects you need. Okay, now I go to the experimental results, quite interesting for strontium luthenate, and you see the strange orientation, 110 orientation. So this orientation means that one axis, C axis, is on the plane of the thin film. Okay, and strontium luthenate, you all know, is a very famous compound. If you warm up the system, you get almost linear resistivity. This is a bad metal. Okay, and there is a ferromagnetic transition somewhere around 160 Kelvin, and paramagnet to ferromagnet transition happens, and also bad metal to good metal Fermi liquid type of transition happens in this compound. And what also changes depending on the thickness, for an example, in 60 nanometer thin film, the Hall effect, anomalous Hall effect, there is a sign change, okay, in this region. This is also known. So what we measured resistance along this direction, and also we measure resistance along this direction by sending current into opposite direction. And what we saw, that along two direction the resistance temperature are different, but as you cool down this divergence is reducing, and the moment you entered into the ferromagnetic phase, this divergence is gone. Okay, and we applied magnetic field to see the resistance change. So in one direction, 001 direction, this is magnetoresistance and this is magnetic field, and near room temperature there is no magnetoresistance. As you cool down, the magnetoresistance comes in, but there is, if you cool down further, the negative magnetoresistance is decreasing. Okay, and also there is a curvature at the beginning, and now it's becoming linear. Now very drastic thing happens in 1 - 1 0. It is negative magnetoresistance near transition temperature. As you cool down, it becomes positive magnetoresistance, and it's even linear. Okay. And so to understand this qualitatively, we fit with the linear model, like magnetoresistance is proportional to magnetic field and magnetoresistance is proportional to H square. Okay, these two contribution. One linear term can come from, you have a ferromagnetic system, if you apply magnetic field, you suppress the spin fluctuation and then the resistance drops. And also in the topological case, band structure, Berry curvature induced linear magnetoresistance also can come. And quadratic term can come from Lorentz force acting on the electrons. So anyway, we fit, and we saw that the quadratic term only inflated near the magnetic transition, around ferromagnetic transition. Left and right, it's gone. And the linear term In the 001 direction, it remains negative. This is most negative near magnetic transition, but it's decreasing, but it remains negative. But linear term in the 1 minus 1 0 direction, it becomes positive. There is a sign change. Okay. Now how to understand the sign change? So of course the sign change can happen because of the linear term. The other term is h square, and the coefficient for the linear term, it comes from spin fluctuations, as I told you, and also the Berry curvature. But you know, is parameter for the spin fluctuations is always negative. Okay, it's not positive at all, it's always negative. So if there is a change in sign happens in A, it must be happening through Berry curvature. So what is the contribution to A? So this is basically the velocity of those mobile charge carriers along a particular direction I, and this is the Berry curvature, and this is the all momentum you integrate throughout the momentum space. So omega and decay integration doesn't change, it's both for the same both direction, it's the same for both direction, but this velocity component along two directions are quite different. That we have found from the density functional theory. We found that in 1 minus 1 0 direction, it's almost 2 times than the other direction, and if you have 2 times larger, then the Berry curvature in 1 minus 1 0 direction is larger, right? And if you have a larger contribution comes in, then you have a chance to see the positive coefficient A from only for the 1 minus 1 0 direction. So overall the effect is coming from the band velocity of the charge carriers along two direction, because, and this is expected, along two direction will be different because crystallographically both are different directions. Okay. So with the Hall effect experiments, we also do anomalous Hall resistance. There is also sign change, you can see this is the green positive, and now it's becoming small, and then it becomes negative. Okay, there is a sign change. This is also known, and we've looked at the resonance region where the resistance doesn't change much. There is a slope always that you cannot see here. You can see here for an example, that is ordinary Hall effect, and this is the anomalous part RSM, and we plot the ordinary Hall effect coefficient. So this is positive near paramagnetic phase, and it becomes negative in the ferromagnetic phase. So this whole dominated contribution to electron dominated contribution is happening, and the transition is around the ferromagnetic transition. And also the anomalous Hall part also changing its sign and becomes very strong below the ferromagnetic transition. There is a sign change. So overall what we are seeing, this is basically our observation, and this is the temperature scale, and temperature scale is inflated around the ferromagnetic transition. First we are seeing the hole dominated response in the paramagnetic phase, and this is near the below the ferromagnetic transition, this is electron dominated. That means there is some sort of bands reconstruction is happening because ferromagnetism is coming in, and this is giving rise to ferromagnetic exchange splitting, and the bands are getting reshuffled. Okay. And what is also happening, this ordinary Hall effect, this is changing, and the this is the anomalous Hall effect is also changing its sign, followed by the ferromagnetic transition, and the sign change is also, sign change in the magnetoresistance is also happening near to the transition. So everything is basically triggered by the ferromagnetic transition in the compound. That's what observation means. And also here you can see this is Fermi liquid regime at extremely low temperature, but near transition in non-Fermi liquid regime. Okay, and due to this Fermi liquid non-Fermi liquid regime that is very different from bad metal, that's why resistance versus temperature is also very similar in the ferromagnetic phase, not in the paramagnetic phase where the bad metallicity is there. Okay, with this I would like to thank my collaborators. We did entire resistance versus temperature magnetoresistance measurements in the IIT Roorkee facility under the guidance of Professor Vivek Malik, and Professor Tulika Mitra did the DFT calculation for strontium ruthenate, and Dirk Fuchs from KIT Germany gave us the strontium ruthenate samples, and these are basically the funding source with which we are continuing. Okay, thank you.
So now session is open for questions.
I have a question about electrical resistivity in strontium ruthenate. You showed the data, and I wanted to ask, where does the existing theory stand as far as your experimental results are concerned? T-square regime for liquid, fine.
Yes.
What about t to the power 0.8 to the power 0.7?
Yeah.
Can it be explained by existing theory?
Yes, so basically what we found, let's go to this t to the power 1, right? This t to the power 1 comes from when electron interacts with the spin fluctuations. This is a theory paper, it's reported, okay? And what we are expecting here, we are not in the ferromagnetic phase, we are in paramagnetic phase, and this divergence is slowly reducing. And now it's, I think, okay to assume that the spin fluctuations part is getting reduced, and whatever the interaction I am having from the electrons is actually electron spin fluctuation scattering, that is giving rise to almost t to the power 1, and t to the power 1 is expected if it is spin fluctuation. Now t square dependence is a Fermi liquid, as you said, it's right, but there is also another term can give you to t square, that is electron and coherent magnon scattering. And magnon you can expect here, right? It's a ferromagnet system, and I believe at very low temperature magnons are coherent. That also gives rise to t square dependence. But if the magnons are not coherent near the transition, then you can go get this t to the power 3/2 dependence. So that's our understanding so far.
Can we say something about elastic and inelastic scattering here? So for example, magnons, these are bosons. So below magnon frequency, typically it's inelastic scattering, so there is exponential freeze out. So what is the typical frequency above which you can say that its t square term comes from there?
So look, the t square term, there are two parts, right? Frequency part and the temperature part, right, in the scattering. But in the simple DC resistance versus temperature measurement, it's almost impossible to talk about the frequency range. Okay, so this is DC measurement, and we are blind to that frequency range.
Okay, thank you.
Firstly, thank you for the very nice talk.
Yeah.
For strontium ruthenate, you showed the anomalous Hall data.
Yeah.
Did you try to extract any signal to see if there is any presence of topological Hall signal?
Yeah, honestly, we did not do. The reason is very simple. Look at our magnetic field. It's only 1 Tesla. And the topological signature not only from the anomalous Hall effect, you should do with the magnetoresistance as well,
right,
where linear part is there. And it is not advisable if the field region is very low, like 1 Tesla. If it is a large field, then definitely you should do.
Okay.
And there are experiments exist, they measured up to 14 Tesla, 15 Tesla, and they found there is a wild point, and that gives rise to large linear magnetoresistance.
Okay, thank you.
Okay, if there are no questions, so let's.
He has a question, I think.
I was just wondering about the dependence of the magnetoresistance signs
Yes.
as a function of temperature.
Yes.
So how does that vary in terms of, so what I mean to say is that not this particular part, I mean one can probably extract this from this curve, but if you look at your first curve where you have these different dependencies, T dependencies.
Yes. Yeah.
So there, do you see much change in terms of the, in presence of magnetic field, do you see much change?
Yeah, so we did the experiment at 1 Tesla, okay, only 1 Tesla because this is dysprosium's candidate. If you apply beyond 1 Tesla, it flies, okay. So with 1 Tesla, there is no change. Whatever curve you are seeing, it's almost similar curve
At all temperatures.
at all temperatures. Okay, it's just overlapping each other, and of course you have to basically zoom it to see only few percentage of magnetoresistance terms. That's it.
Yes.
Okay. Thank you, Professor Sen.
Okay.
So,